Beyond the habitable zone. The search for life in exoplanet atmospheres. The search for life beyond Earth begins with identifying planets capable of hosting liquid water. Astronomers traditionally focus on a star's habitable zone, the region where temperatures allow water to exist in liquid form. However, a planet's location within this zone is just the first step. The real key to habitability lies in its atmosphere. The limitations of the habitable zone. The habitable zone is a useful starting point, but it's not a guarantee of life. Factors like geological activity and atmospheric regulation play a critical role. Venus, though currently scorching, may have once held water, while Mars shows evidence of ancient lakes and rivers despite lying just outside the habitable zone's outer edge. This demonstrates that the zone isn't a rigid boundary, but rather a guideline. Why atmospheres matter. A planet's atmosphere determines its surface temperature through the greenhouse effect. Gases like carbon dioxide and water vapor trap heat, keeping Earth warm enough for liquid water. Without an atmosphere, Earth would be frozen solid. The habitable zone's boundaries are defined by the necessary greenhouse effect to maintain liquid water. The question now shifts to whether other planets have similar climate-regulating processes. Planetary processes and long-term habitability life requires more than just temporary liquid water. It needs long-term stability. Earth's climate has remained within habitable ranges for billions of years, allowing life to emerge and evolve. This stability is maintained by a natural thermostat, the carbon cycle. Volcanoes release carbon dioxide, warming the planet. Rain and weathering remove carbon from the atmosphere, storing it in rocks and oceans. Cooling temperatures slow this process, allowing carbon dioxide to build up again. This cycle has helped Earth recover from ice ages and avoid runaway warming, even as the sun has brightened over time. The key question is whether this process occurs on other planets. Detecting planetary processes from afar. Scientists are now seeking to detect these processes remotely. By observing many rocky planets in habitable zones, they can look for patterns connecting sunlight received and atmospheric carbon dioxide levels. A consistent correlation would suggest similar carbon cycling processes are at play. Atmospheric composition can also reveal geological activity. For example, the presence of shifting tectonic plates, like on Earth, can be inferred from atmospheric data, as these plates drive volcanism and weathering, which regulate carbon levels. The future of exoplanet research. The next step involves analyzing atmospheric data from a large sample of rocky planets to identify trends indicating underlying planetary processes. Comparing these patterns with habitable zone position will determine whether the zone accurately predicts habitability, or if some planets maintain liquid water outside its boundaries. This approach is crucial given the diversity of exoplanets, including super-Earths and mini-Neptunes orbiting smaller, cooler stars. NASA's upcoming Habitable Worlds Observatory will directly image Earth-sized planets around sun-like stars, analyzing starlight filtered through their atmospheres to detect gases, like carbon dioxide, methane, water vapor, and oxygen. These compounds will reveal crucial insights into the processes shaping these worlds. The search for life beyond Earth is no longer just about finding planets in the right zone, but about understanding the complex interplay between a planet's atmosphere, geology, and long-term climate stability. The next generation of space telescopes will provide the data needed to answer this question, bringing us closer than ever to discovering whether we are alone in the universe.